This is my discussion about SAP 1 or simple as possible computer. I'm Jimuel Nyle Mallari from BSCPA 4A. First, the simple as possible or SAP 1 computer is a very basic model of a microprocessor explained by Albert Paul Malvino. The SAP or simple as possible 1 design contains the basic necessities for a functional microprocessor. Its primary purpose is to develop a basic understanding of how a microprocessor works, interacts with memory and other parts of the system like input and output. The instruction set is very limited and simple. Uh, in program counter, we it has a 4-bit wide. The program counter's job is to store and send out the memory address of the next instruction to be fetched and executed. The program counter, which is a part of the control unit, counts from 0000 to 1111 as the program is stored at the beginning of the memory with the first instruction at binary address 0000. The second instruction at address 0001, the third at address 0010, and so on. At the start of each computer run, the program counter is reset to 0000. When the computer run starts, the program counter sends out the address 0000 to the memory and is then increment by 1. After the first instruction is fetched and execute, the program counter sends the next address 0001 to the memory, and again after that the program counter is increment. In this way, the program counter keeps track of the next instruction to be fetched and executed. Second is input and MAR or memory address register. It includes the address and data switch registers and send 5 address bits and 8 data bits to the RAM. The MAR stores the 4-bit address of a data or instruction which are placed in memory. When the SAP1 is running, the 4-bit address is gotten from the program counter through the W bus and then stored. This stored address is sent to the RAM where data or instructions are read from. A RAM. It has 16 by 8 RAM or random access memory. The system I am simple as possible one makes use of a 16 by 8 RAM or random access memory. It has 16 memory locations, each storing 8 bits of data. The RAM can be programmed by means of the address and data switches, allowing you to write to the memory before a computer run. In this way, the instruction or data word stored in the RAM is placed on the W bus for use in some other part of the computer. that is RAM. Third one is a fourth one, instruction register. Loads the content of the address memory location through the W bus. Upper nibble goes directly to the controller sequencer. Lower nibble is read into the W bus when needed. Instruction register receives and stores the instruction placed on the bus from the RAM. The upper nibble is a two-state output that goes into the controller sequencer, while the lower nibble is a three-state output that is read from the bus when needed. In controller sequencer, it has before each computer run. CLR, signal sent to PC, resets the program counter 00000. CLR signal sent to IR wipes out the last instruction in the IR. CLK signal sent to IO buffer registers synchronize the operation of the computer. And the last one of the control sequencer, CLK signal to PC. The controller sequencer sends out signals that control the computer and make sure things happen only when they are supposed to. The, the next 12-bit output signals from controller sequencer is called the control word, which determines how the register will react to the next positive clock edge. It has the following format: CON equals CP EP through LM through CE through LI EI LA EU SU EU LB LO. The 12 bits that comes out controls the rest of the computer. The 12 bars carrying the control word is called control bus. This is the block diagram of simple as possible one. It's the first stage in the evolution toward modern computers. We can see the block diagram. It has a program counter, input, accumulator, other subtractor, P register, output register, binary display, control sequencer, instruction register, and RAM. This is the architecture of a system as possible and microprocessor computer. Simple as possible computer, or SAP. The type of computer is specially designed for the academic purpose and nothing has to do with the commercial use. The architecture is 8 bits and comprises of 16 by 8 memory, 16 memory allocation with 8 bits in each location. Therefore, need for address lines which either comes from the PC program counter, which may be called instruction pointer during computer run phase, or may come from the 4 address switches during the program phase. All instructions, thus 5 only, get stored in this memory. It means SAP or system simple as possible cannot store program having more than 16 instructions. The accumulator The accumulator is an 8-bit buffer register that stores in intermediate answers during a computer run. The accumulator has two outputs. The two-state output goes directly to the other subtractor, and three-state output goes to the bus. The accumulator have buffer register 8-bit wide. When E or A is high, the content appears on the W bus. In other substructure, the other substructure asynchronously adds to or subtract a value from the accumulator depending on the value of SU. It makes use of 2's complement to achieve this. When SU is low, the output of the other subtractor is the sum of the values in the accumulator and in the B register. When SU is high, the output is difference between them. It has 2's complement other subtractor. This module is a synchronization clock, which means that its content can change as soon as the input words change. In B register, it is 8-bit buffer register which is primarily used to hold the other operand. One of operand is always accumulator, take note of that. Of mathematical operations. In output register, these registers hold the output of out instruction. When the word itself output, it is the outside of instruction or out. The answer that is stored in accumulator is loaded into the output register through the W bus. Binary display. It is a row of 8 LEDs to show the contents of output register by and binary display unit is the output device for the SAP1 microprocessor. In the binary display shows us the contents of the output by connecting each LED or LED to the output of the output register. This therefore enables viewing of the answer transferred from the accumulator to the output register in binary. Here the sample of logic design. First, in this program counter, we see the flow of the words or sub logic and RAM. We have RAM, input and memory address register, instruction register. Next is controller sequence with 7 segment display to view control word in X. This is accumulator, other substructor B register, and output register 7 segment display driver for hex display. The Cortical will forward by enum into more readable hex format. SAP 1 instruction cycle. SAP 1 instruction set consists of the following instructions. In mnemonic, have LDA in this operation. The LDA load address memory contents into accumulator, and the OP code is 0000. In add address memory contents to accumulator. In, in OP code, the add is 0001. Sub, on the word subtract address memory contents from accumulator. In OP code, it is 0010. Out, load accumulator data into output register. In OP code, it is 1110. HLT, in operation, stop processing. While in OP code, it is 1111. The instructions format of SAP 1 computer is XXXX because we have not code, or it is example of what the first 5 bits make the OP code while the last 4 bits make the operand address. Machine cycle and instruction cycle. So SAP1 has 60 states, 3 fetch and 3 execute cycles reserved for each instruction. Not all instructions required all the 60 states for execution. The unused T-state is marked as no operation or NOP cycle. Each T-state is called a machine cycle for SAP1. A ring counter is used to generate a T-state at very falling edge of clock pulse. The ring counter output is reset after the 6th T-state. In fetch cycle, T1 and T2, T3 machine cycle. Execute cycle has T4, T5, T6 machine cycle. Complete code includes OP code and operand. One instruction is executed in one instruction cycle. Instruction cycle may consist of many machine cycles. For SAP1, instruction cycle equals machine cycle. Instruction cycle equals fetch cycle plus execution cycle. Fetch cycle is generally same for all instructions. Complete code includes OP code and operand like LDA 04800000100. One instruction is executed in one instruction cycle. Yeah, this is the figure of instruction cycle. The flow of the instruction cycle or machine cycle, fetch and execute. That's the figure of instruction cycle flow. Fetch and execution cycle of SAP instructions. SAP1 instruction cycle 3 clock cycles to fetch and decode base 3 clock cycles to execute. The first 3 states are address, increment, and memory. Controller has a 6-bit ring counter which continuously cycles from 000001 up to 100000, then resets. Take note, must be set to 000001. when we initialize the computer. Mm, And ring counter is clock on the clock high to low transition. Most of the other circuits in the computer on clock low to high transition. Fetch cycle address state. You have to enable PC to bus 3 state output and may MAR or memory. What's that memory? Memory address register. Okay, load line. In increment state, you have to enable PC increment and perhaps wait for memory access time. Should wait for and take patience. Memory state. In memory state, enable memory CE and IE IR load line. IR is loaded on the low to high clock transition, so stabilize before state 4 is entered. The plus 1 MAR greater than PC. T2 81 T2 PC greater than PC plus 1. T3 IR followed for RAM. It is to connect them to loaded on the low to high clock transition. Execution cycle or add and add. State 4. Enable IR to bus 3 state output MAR load line. State 5. Enable memory CE register B load line. State 6. Enable add ALU to bus 3 state output accumulator load line. T4 MAR IR address of B. T5B enable to RAM. T6 accumulator plus B. Controller implementation. How to generate micro words. If a bit is only on during one cycle, connect it to the corresponding ring counter bit. If a bit is only for an instruction, connect it to the instruction as decoded by a 4-bit 1 of 16 decoder. If a bit is only on for an instruction and a cycle, connect it to the end for the ring counter bit and the decoder output. If a bit is on for multiple instruction and or cycles, work out the truth table and use and or multiplexers to implement it. Alternative, use a RAM. That's my discussion for the SAP 1 or simple as possible computer.